Hello my dear students, this is Akash HD and welcome to the HD physics classes. Hope so you are doing really great. So students, in this video we are going to calculate the electric potential due to the conducting sphere, and we will understand that whether the conducting sphere is solid or hollow does not matter. Even in the case of electric potential, whether the charge is uniformly distributed or the charge is non-uniformly distributed, the potential value will not change, because potential is which kind of quantity? It is the scalar quantity. So students, let's start the video and let's learn the electric potential due to the sphere and concentric spheres also. Okay, so let's start it. So students, you can see very well, we are going to see electric potential due to different bodies here. So what is there? See, electric potential due to a charged solid conducting sphere or thin cell. Why I am telling solid? Or solid means okay, anyhow solid only, but hollow means inside what is there? The mass is not there. Why students? Because this is the conducting sphere, and remember that the charge will be always on the surface of the conducting sphere. That's why solid or hollow does not matter. Okay, so what we are going to see? We are going to find out electric potential some different points like outside, on the surface and inside, and we'll draw the graph also. So see here, let charge Q is uniformly distributed on a conducting sphere of a radius r. You can see no, one conducting sphere is there, charge on the surface, how much charge? Q, and radius how much? R, as shown in diagram. Electric potential due to the sphere at different points can be calculated as different points, as I have told you, outside, surface, inside. So at an external point is there. So here students, see, let's take, I have taken point A. This is the center. This is the center here, no? And this is observation point. So center to observation point, we will tell position vector r. Scalar, na? So only we'll just take the magnitude, just like a distances. So here you can see very well by seeing the diagram also. This small r is greater than capital R. What is small r? Always center to the observation point distance. Okay, in a vector form, position vector and all is there. Okay, so r greater than r. So what happens that in this situation, whenever my observation point is outside, the total charge of the sphere can be concentrated at the center. Where concentrated? At the center here. And this distance how much here? R, and here I want to calculate the potential A. So you know very well, potential due to the point charge, formula very well, electric potential. So what we can write here, students? Outside, or we can tell at point A is given by 1 by 4 pi epsilon naught into Q by R. This is potential where? Outside, outside. Now if in case, in second situation, our observation point is here, at the surface or just outside here. So what will happen that in this situation, this small r will be how much? Capital R. Okay, that we are going to see next one here, at the surface or just outside. What will happen that here? This small r will be equal to capital R. That means potential at point B or at the surface is given by 1 by 4 pi epsilon naught into Q by capital R. Here also, the total charge can be concentrated at the center whenever the observation point is outside or on the surface, no problem. Now, the main thing arises, this one here, at an internal point. So here again, we have taken, you know very well, no? So here I have taken one point here. Now, let's take this point is C. And this center to, okay, already C is taken, the center. Okay, so let's take here, I have taken point D, no problem here. And this distance how much here? R. And this is the center C. So what happens that here in this situation, we have to just use the relation between electric field and potential. So what will happen that students here, you know the formula, S, say this, dV equal to minus E dot dr here. Okay, so students, you know very well, as electric field inside this is how much here? Electric field inside how much? Electric field inside this will be how much? 0. Even we can use the Gauss law also. Let's take for example here I have taken one imaginary sphere is there. Okay, so what is there? Inside this electric field how much? 0. Okay, so what will happen that here I can write here, see, this dV is equal to minus integration electric field how much here? 0 anyhow, 0 into dr, anyhow 0 is there, and we'll put some limits also. Let's take for example here, we'll see here, see, when small r equal to where? When we are small r equal to capital R. Capital R is where, students? At the surface. And at the surface, how much potential? Potential is Vs. So here I will write here Vs, surface potential. And here at point D, how much is there? R. Okay. And here potential how much here? Let's take here V in, Vd or V in. So students, when you will simplify this, what this will become here? Integration of dV means how much here? V, and here Vs, here V in, and integration of 0 dr here, very basic, 0. That means what we can tell here? This will become V in minus Vs equal to 0. Hence we can tell inside potential is equal to surface potential, and how much formula is there, students? 1 by 4 pi epsilon naught into Q by R. This is the formula. Okay, inside all the points. Even you take any point. Let's take, for example, I have taken a D is there, and I have taken G, H, K, any point I take. So whether G is there, H is there, K is there, all inside now. So potential will be how much here? Same, 1 by 4 pi epsilon naught into Q by R. This is pi, not a Z. Okay, remember that here. Now, great. Just here, very well. Now, remember that. And especially the graph is very, very important. Graph. Anyhow, this space no need, already we have proved before itself. Now, so now here, see students. So again, let me write here. As what we have done, this V out. V out was how much here? 1 by 4 plus or not. Let's take K. So K into Q by R. So we can tell, students, this V out is inversely proportional to R. Okay. At the surface, how much? At the surface, K into Q by capital R, and inside how much potential? Surface potential. And how much here? K into Q by R, constant value. Which value? Constant value. Okay. So let's here please. Now here is there. Now let me change the color. So students, this is the center anyhow. This one, how much there? Is small r equal to capital R. Here is small r equal to how much? Minus R. What is small r? Center to observation point. Remember that here. Now this is R, and anyhow this is minus R, you can tell. In a very plus x minus x, but we are doing in a general way. So what happens that here? This one represents inside. Okay. So see here please here. This is the surface. Potential Vs. You know whatever potential, not surface. Surface is where? Yes, surface is here. Whatever potential at the surface is, this is the surface here. Surface, so we have to represent here Vs. So what happens that here, whatever potential at the surface, same potential inside. That means this graph will go like this here. Whatever potential at the surface, same how much here? Inside. If we see outside, inversely proportional to R. That means it will go like this here. Positive charge is there, so only the graph is coming above the axis. If in case negative charge is there, the graph will shift down the axis. Please remember that. And here V out inversely proportional to R. Here also V out inversely proportional to R here. Okay, and this side V, and anyhow this side R is there. Now, can you see it very well? Graph is very, very important for the positive charge. And I told you, negative charge is downward. Remember that the graph. Now students, we will see some applications. See here the application. What are the applications? Electric potential due to concentric shells. So see here please, for two concentric shells. So students, here you have to remember one basics. Whatever potential at the surface, same potential where? Inside. And second basic is that whenever the observation point is outside the cell, total charge can be concentrated where? At the center. Okay, students, so let's see here. I have taken, for example, point A here. Okay, and this distance how much here? This distance, let's take RA. So potential at point A. What I am telling students? Potential at point where? Potential at A. Potential at A. So students, remember that here. Potential at A is given by potential at A due to first one. Let's take this is first one and this is second one. So we can write here. This is potential at point A due to first one, VA1 plus potential at point A due to 2. So students, just tell me here. Point A with respect to 1, outside or inside? Outside. Out. Potential at point A due to 2 also? Outside. So whenever outside is there, we have to use the actual length here. So what it will become here? Let me just write here directly. K into Q1 by distance how much here? RA plus K into here how much charge? Q2. K into Q2 by again RA. Okay. So this is the thing is there. See here. This I have written. Where potential at point A. Similarly, let's take here. Now I have taken some other point. Let's take I have taken point B here. Now, and this distance how much here? This distance is RB. Very important in exam. Okay. So now we are seeing students potential at B. Potential where? Potential at B. So see here. Potential at point B means VB1 plus VB2. Okay, now let's see. So point B with respect to 1, this is 1. Point B is where? Outside or inside? Outside. Okay, and potential at point B due to 2 is here, B is here, that means where? Inside. And whenever inside is there, we have to take which potential? We have to take the surface potential. Okay, so what values will come here? It will come here. Outside means K into Q1, actual length we have to use. How much length is there? RB. So K Q1 by RB plus K into Q2. Where? Inside. That means which potential? Surface potential. Whatever potential at the surface of 2, same potential inside. That means which length we have to use? We have to use K into Q2 by R2. This is potential at point B. Okay, so see, we have done here. This one we have done for which one? 2 concentric shells. Third one, let's take here. No, diagram is looking a little bit complex, but here I just want to make you understand all these things again in a beautiful way. So see here please. For 3 concentric shells, again I will just take some points here. Let's take, for example, now I have taken point here. Here I have taken point. Okay, and let's take, students, this point is A here. How much point is there? The point is A. Okay, this one. And this length, how much here? This length is RA. So students, first one, see here again. Potential at point A, that means VA, how much here again? VA1 plus VA2 plus VA3. Why? Because how many is there? 3 is there. Now, students, again let's give a name here. This is first one, anyhow this is second one, and this is third one. So you can see very well, point A with respect to shell 1 is where? Outside. Which one? Outside. Similarly, point A with respect to shell 2, that is also outside. But point A with respect to shell 3 is where? Inside. Inside means which potential? Anyhow, again I am telling surface potential. Now, you know very well. What will happen at here? K into charge Q1, actual length. Outside means actual length. How much there? RA. Plus negative charge is there. For your basic understanding, I have written here. Again, outside means which length? Actual length. Plus K into Q3. Whatever potential at the surface, say potential inside. That means which length we have to use? This R3 length we have to use. Okay? I hope so you have understood very well. Let's take, for example, one more. Very easy. Let's take, I have taken point here. No? Point B is here. And let's take this distance, how much there? RB. I want to calculate potential. So students, see, now potential at point B means VB1 plus VB2 plus VB3. Now if you will observe the diagram very well here, point B with respect to 1, inside. Point B with respect to 1, inside. Point B with respect to 1, inside here. That means which potential we have to take? Surface potential. Surface potential of first, surface potential of second, and surface potential of third. Very easy. Now, so here please. K into Q1. Surface potential of first, how much here? We have to use this actual length, R1. Plus K. Surface potential of 2, how much here? Which length? This radius. For 2, how much is there? R2. Plus for third one, K into Q3 by R3. Okay? Very well. Understood, I think so? Very well.